We solved this shortest path problem using the Dijkstra algorithm in the previous video, where the source node was 1, and in that case we don't mention which node is the destination, because even if a destination is given, the Dijkstra algorithm will find the shortest path from node 1 to all nodes, because it needs to check all the vertices and find the final solution simultaneously for all the vertices. It means that if I want to find the shortest path from 1 to 2, I cannot say I don't need to check 4 or 5, because there might be a path coming from 4 or 5 to 2, and that may have the lowest cost in comparison to the others. But in this algorithm that we study here, and we want to use solver to solve as a linear programming model, a source and a destination must be given. For each time, we just find shortest path from one node to another one, not all the other nodes. We see 3 different examples here. Once we want to find the shortest path from 1 to 5, this is the one exactly we did in last video. We will check the answer, we can compare it. Another time from 2 to 4, and in part C we want to try to find the shortest path from 3 to 2. But without using the algorithm and solving as a linear programming model, we can check it because it's a basic network. We can see that here from 1 to 5. We can check all the possible passes. I can start from 1, go to 2, and then 4, and then 5, this pass. And the cost for this is going to be equal to 2 plus 5 plus 1, which is 8. Another pass, let's say this is pass 1. For path 2, we can start from 1, go to 2 again. But from 2, we don't go to 4, we go to 3. And from 3, we directly go to 5. For this one, the cost is 2 plus 3 plus 3. Again, 8. 3, 3, and 2. Pass 3, we can go from 1 to 2, 2 to 3, but this time from 3 we can go to 4, and 4 to 5. And in this case, the cost is going to be 2, 5, 6, 7. And there exists another passes like P4. We can go from 1 to 3, then 3 to 5 directly. The cost is 6 plus 3, 9. And P5 from 1 to 3, 3 to 4, and then 4 to 1, 4 to 5. In this case, we have 6 plus 1, 7, plus 1, 8. And finally, we can see that this is the shortest path that we found in the previous video by Dijkstra algorithm. And right now, we will solve as a linear programming model, or better to say, as the mean cost flow problem. Now let's see what we can say about the shortest path from 2 to 4. From 2 to 4, we can start from 2 and go to 5 directly. So this time the length of the path is going to be right here. From 2 to 4, let's say this is A, 4B. From 2 to 4, we can start from 2 and go to 4 directly, then the cost is 5. From 2, we can go to 3 and then to 4. In this case, the cost is 4. And there's no other way, because if we go to 3, we cannot go to 1. And if we go to 5, again, there is no outgoing to 4. In this case, this is the shortest path. In part C, we want to start from 3 and go to 2. From 3, I cannot go to 2 directly, and we cannot move to 1. If we go to 4, from 4 we can go to 5, and there's no ending for this. We cannot continue and find 2 or reach 2. From 3 also we can go to 5. Again, there's no outgoing arc from 5. So in this case, there is no path. So we say that the shortest path does not exist in this case. And our algorithm must give the same answer. Now, how we can consider our problem as a net or mean cost flow problem on a network. So this is the same network on the same graph. And let's consider the first case. We say that source is 1, destination is 5. We want to find this one. So we see that the same problem can be considered as the mean cost flow problem for sending 1 unit of commodity from source to destination. Since this is similar to the transportation problem, but since we are working on a graph, then we don't see which is row or column as transportation tableau. Based on that, we write positive values for supplies, negative values for demands. And we want to find the minimum cost for this, let's say, transportation problem. Now, as a transportation problem, I want to minimize the cost. What's going to be the cost? First of all, let's see the decision variables. So decision variables are going to be xij. If we decide to go from 1 to 2 or send this 1 unit of commodity from this way or this arc, then we have the value 1 for it. Otherwise, 0. Let me write that one place. I'll say xij's are going to be 0 or 1. 1 means this arc is selected, 0 is not selected. If it is selected, we can multiply this 2 by that 1. It means that going from 1 to 2, similar to finding the shortest path, there is this length or there is this cost for us. Again, if I give x2 to 4, 1, it means that we are moving from 2 to 4. And if this one also, x4 to 5 also is 1, then we can reach from 1 to 5. Or if we come back and see the previous passes here, for example, for this P5, this 1 and 3, it means that we are moving from 1 to 3. It says that x13 is 1. From 3 we go to 4, x34 is 1. And from 4 we go to 5, x45 is 1. And the rest of the xij's are zeros. Now if I multiply all xij by this cij, so these are cij, for example, this is c12. Xij multiplied by cij's, that sum is going to give us the sum of these ways on the arcs, which is the cost for the shortest path. Now let's see how we can write. This is the objective function. So objective function is going to be the product of cij's, xij's, or some product of, let's say. So we are going to have 2 times x12 plus. From 1 we can also go to 3 by cost 6 times x. Let me write a little bit this way that we can write in one row. Well, it's going to be too long. 6 times x13. And then we start from 2. We can go to 4 by cost 5 times x24 plus 3 times x23 plus. Now if we are at 3, we can go to 4 or 5. To 4 we have 1 times x34 plus 3 times x35 plus. If we are at 4 again, we can go to 5 by this cost, 1 times x45, and there is no outgoing arc from 5. So this is the objective function. We want to minimize it, subject to the conditions. From 1, we have 1 unit to supply. We should send it out because we need that one here. So the condition for node 1 is going to be the outgoing means x12 plus x13. So if I write x12, it means that sending from node 1 to node 2. x12 is 1. It means that we are going this way, or we are sending that 1 unit of commodity from this path. This must be exactly 1. For the other vertices, you can see that we wrote bi0. It means that they don't supply anything and they do not demand any value. Anything that they receive, they should send out. So for node 2, incoming must be equal to outgoing. So I can say that what we send out, or let's say x24 plus x23 must be exactly equal to what we received at 2x12. This is for node 2. For node 3, what we send out, which is going to be 3 to 4, 3 to 5, must be exactly the one that we received. But this time we have two of them. We can receive from 1 or 2. Anything we receive, we should send out. For node 4, the same. From 4, we should send to 5. Anything we receive from 2 to 4 or from 3 to 4. And finally, for the destination, there's no outgoing, there's only incoming. So incoming must be equal to 1. Incoming equal to 1 or 1. Let me write the same. Incoming, which is x3 to 5 plus x4 to 5 must be equal to 1. We should receive these two from the sum of values that we receive must be equal to 1. It means that one of them is 0, the other one 1 for sure at the final answer. And xij is 0 or 1. So if a problem like this is given and we ask to write the linear programming model, you should consider all PIs by yourself based on the given source and destination, and then write the objective and the constraints. But if we want to write all these things in general, we can see that whatever we wrote here, we can move all the variables one side, and if you want to keep right hand side positive, then right hand side the same as the values on the vertices. We can see that this is exactly the sum of outgoing from 1 must be equal to 1. If I move this one to the left, it's going to be the sum of incoming, outgoing minus incoming equal to 0. So here I can say that this is the sum of all edges, outgoing minus incoming must be equal to 0. Outgoing minus incoming 0. Outgoing minus incoming is 1 for source, and outgoing minus incoming for the destination is negative 1. It means that if I multiply this by negative, it's going to be, since there is no outgoing, minus incoming. If I multiply this by negative sign, it can be minus x35 minus x45 equal minus 1. Since there is no outgoing and incomings must have negative sign, and the sum of the algebraic sum of outgoing and incoming, outgoing minus incoming, must be the value on the node, which is minus 1. Now, we try to write all this information in an Excel file and start to solve the problem. So this is the same problem that we had. And we want to solve A, B, C, and finally we will give the shortest path here. We are going to write the shortest path here. For the first case, A, what is the source? We said that source is vertex 1 and destination is vertex 5. We are solving this one. But for all of them, all the calculations that we are going to do here are going to be all the same. Only in the constraints we will change the source and destination. The rest will remain the same. So what is the cost matrix? We look at the graph and write the values here. If there is an arc from node 1 to node 2, we highlight that cell. It means that we have only these arcs in our graph. The rest does not exist. But since we are working in a rectangular form or the matrix form, then the algorithm or the problem may select these cells also as a solution or give a value for them, and we want to avoid to selecting these cells and giving xij equal to 1 for other values. Now first we write these values here. What do we have there? 1 to 2, the cost is 2. Then 1 to 3, it is 6. And then we have 2 to 3, the cost is 3. 2 to 4, the cost is 5. And from 3, look, we are moving from row to column. From 3, we can go to 4 or 5. 3 to 4, the cost is 1. 3 to 5, the cost is 3. And from 4, we can go to 5 with cost 1. And from 5, we cannot go anywhere. So last column, last row, we have nothing. So these are some values that we have. This is the cost matrix based on the graph, but we want to modify it and write some values here that we are going to give a name for that big M, or if we have this Cij as a large number, then it's going to penalize the objective function and avoid to give the value 1 for this xij's. So what is the big M? First of all, we write the value of big M. Big M is going to be equal to sum of, we can give any large number, very large number in comparison to the values here, but we don't need to work with very big numbers. We can just add these values, the sum of allCij's on the given matrix. And we add 1, we can add any other number to have a big number, but 1 is enough. And I will tell you why we add that 1. So why do we add 1? Because if we have to select all the existing arcs to find the path, in the worst case, we may select all the arcs. If all the arcs are selected, the total cost is going to be the sum of theseCij's. But if we select any other non-existing arc like this, then we need to give a big M to that cell. And in that case, since the value of that cell is going to be in variables, it's going to be equal to 1. 1 times this big M is going to be larger than the sum of those values. And we can write a condition for that, not to accept the z value to be greater than this value. And it will avoid to select or give xij equal to 1 for the non-existing arcs. So this big M, just some of these values. Now, I want to bring those values here, the existing arcs, and for non-existing arcs, I want to give this big M. So I want to write a formula here. And since it's for an array, we want to find all the values at once, then you need to select them all like this. And then start to write the formula equal. What is the conditional? I want to check what condition I want to see. If in this matrix I have a blank, it means that we don't have such a edge, then we need to give a big M as a Cij for that. So I say that if is blank is a function, checks whether this cell is blank or not. If this cell is blank, so it means that if it is true, then I'm going to write that big M there. Otherwise, the value of the cell itself. So if this cell, so you need to select all the matrix at once. If is blank, this cell, then it means that if it is true or the cell is blank, then I'm going to give this big M. But for this big M, it's better to lock it, because if we want to go to the other cells, it may move, then I need F4 to lock that cell. Otherwise, the value of the same cell, then I select this one. And since we are working with formula for an array, we are writing a rule for an array, you need to, when you finish your formula, you need to press and hold Ctrl and Shift and then press Enter to have all the values like this. Now you can see that we have 22 wherever we had blank. For the other cells, we have the same value, their own value. It means that if I want to use or change some of these values on the edges here, for example, if I change this 1 to 10, then big M is going to change to some value like 31. All 22s will change to 31, and that one also change to 10. And for example, if I have an arc here with a negative cost, or it is 0, still it will remain 0, and big M didn't, however, I changed 1 to 0, became changed to 30, and all the others. So let's bring them back. Here we had 3 to 4, the cost was 1, and 4 to 5 also the cost was 1. Now we came back to the original value that we had. We call this one, the first one, cost matrix, and this is the modified cost matrix that we gave a big M to penalize the non-existing arcs. Similarly, we can copy and paste this empty matrix to keep this highlighted places, but in this case I put another color here to show that these are variables, and these cells are cells that we can give the value 1. We can select these cells to show the shortest path. Now these are the cells that we want to keep the value of xij's. It means that they are going to be 0 or 1. But what are the conditions for each vertex? For example, for vertex 1, if I read this value, it is x11, 12, 13, 14, 15. It means that the sum of all outgoing from 1, so I want to write here, equal sum of these values. This is the sum of these values. So this is the outgoing. How about incoming? Incoming to 1. I can come from 1 to 1, 2 to 1, 3 to 1, 4 to 1, 5 to 1. So the value that I'm writing here, this is incoming, and that was outgoing. So this is incoming to 1. So here we write equal sum of these values. You may see this green rectangle here. It says that there is a number next to the range that you selected, but you are not using that. There might be a mistake, okay? It's not important, you can ignore it. Now, this one, you can click here and then ignore the error. It disappears. But even if it remains there, it doesn't matter. Now I copy this rule down, and this one also to the right. And now let's check whether the rule works properly or not. For example, if I have a 1 here, another 1 there, and another 1 here. What do I have? In this row, I have a 2 here. In that row, a 1. The rest are zeros. In this column, we have 2. Here also we have, however, we are not going to have 2. They are going to be 0 or 1. Now, what else? Now, I want to write the outgoing here because we want to write outgoing minus incoming. I want to bring those values here. Look, we know that we can copy some column and paste as a row, but if you do like this, it will not work. Let's see. If I copy this, but I paste here as transpose, then you will see that here I have a 4, but I don't have a 4 there. And if you click on this, you will see that this is not the sum of the values in the row. It's going to change to the column because you are pasting as transpose, and it adds this 2. It moves down, so it says that copying and pasting as transpose does not work in this case. Now I delete this one, And you can see that. In a case like this, if I have a row vector or column vector and I want to convert it to row vector, we know that we can find the transpose of that matrix or column vector. So you need to write transpose of this column. Now you can see that this 2 here is exactly this one. Or if I click on this, it's going to be the value of this cell. Okay, exactly. If I write something, for example, another 1 here, then this sum is 3 and the same 3 is here. So originally there is nothing inside the variables here. These are all zeros, or we have no value there. Now basic rule here, equal outgoing, which is this one, minus incoming, this cell. And now I can copy this to the right. So these are rules. We have a formula here. This one is outgoing minus incoming. Now, the question in the part A says that 1 is source, 5 is destination. So for source, we knew that BI is 1. For destination, BI is minus 1. All the others are zeros. So I have a 0 here. Or I can select them all and say these are all zeros. Let's see. If I want to give zeros here, I can select like this and say equal. All of them are 0. But again, since you are using, if you press enter, only the first one becomes 0. But if you want to all to change to 0, or this give the same value for all of them, you should give again the use control shift enter to use the array method. Equals 0, but control shift enter, I want to change all of them to 0. Now that's fine. What remains now? Finding the objective function. So objective function isCij's, Xij's, and we know the rule for that, which is sum product. Now I need to write sum product ofCij's, but the modified one, and Xij's. So modifiedCij's are here with Xij's, which are here. This is our objective. For now it is 0 because all Xij's are 0. And here also we write equal whatever we found in big M minus 1. Why I subtract 1 here? Because I know that the total cost must be less than 22, or that big M. If it is big M or greater than big M, it means that one of these non-existing arc has been selected. Since we don't have less than sign in solver, then I subtract 1 and write less than or equal to 21. It should be less than big M, but I change to less than or equal to big M minus 1. Now we are ready to go to solver, selecting this cell and calling solver to solve the problem. Now we open the solver. So where is we want objective function is here. We want to minimize the objective function. Changing variables are here. And now we want to add the variables. What variables do we have? First of all the variables, we say that Xij's are 0 or 1, so they are all binary. We can say integer, but since they are 0 or 1, then we select binary. Another constraint. This outgoing minus incoming, this vector, must be exactly the values on the vertices or BIs. Anything else, we have one more condition to add, and it is the objective must be less than or equal to big M minus 1. And that's all. We solve by solver, as a simplex method. Select the simplex. And again, we have this non-negativity. However, since they are binary, then 0, 1, then it will work automatically. Now, if we press on solve, you will see 7, exactly the one that we had in the shortest path that we solved right now, and also we found by Dijkstra algorithm. Now, if you see exclamation mark here, you may not, or Excel may not find the feasible solution. The problem may not be feasible. Then don't press OK. In that case, we will discard the changes. One of the parts from ABC is infeasible, or we don't have a shortest path from, there's no path from, I guess 3 to something like this. Okay. Now this is the total cost, but what is the solution? Let's look at this green part. We can see that in the white part, we are not going to have any ones based on this condition that objective cannot be more than or greater than or equal to big M. Now from this ones, we can see that we are coming to 5 from 4. We are coming to 4 from 3. We are coming to 3 from 2. And we are coming to 2 from 1. That is the shortest path from 1 to 5. Exactly the one that we wanted to find. And this is exactly the one we found by Dijkstra algorithm. And here also we see the same thing. So here we need to write these values. In part A, I say that I should start from, however, we could start from the first part of the matrix. In the first row, we had a 1. It says that we are moving from 1 to, we are moving from 1 to 2, like this. And then from 2 to 3, 3 to 4, 4 to 5. This was the shortest path, and the total cost with the cost equal 7. This was the shortest path for part A. Now we can do the same for part B and C, but this time it's very easy because everything is ready. We are just going to change this source and destination, nothing else. So we continue by part B. In the part B, source is 2, destination is 4. Now I change these values to 2 and 4. And we go down here. Source this time is 2. Source is 2. And destination is 4. Just right here. So this is source, that's destination. Since this is source, then I copy this or just move this one there. We can move it. No problem. Then let's just keep the same formatting. So this is going to be 0. Source is 1. And maybe, oh, this is a part of an array, sorry. Which part is a part of an array? So 0, 0, 0, 0. Now this is -1. But we didn't use formula in this cell. Doesn't accept this. Let's delete them all. Maybe. Now let's write 0. Now, since, yeah, I remember now. When I wanted to create those zeros, we used the array formula. Because of that, we couldn't change one by one. Now this is 0. This is 1, 0. This destination is -1, and this is 0. That's all. And no other change. Let's remove these things. However, if they are there, still the solver will solve. The change is only in this row. We change the value of bi's. Now we go to solver and solve by the same rules and see that it's going to be 4. And what is the solution? The solution here says that we want to go from 2 to 4. So here we start from 2, and this one says you should go from 2 to 3. And now if I'm in 3, I can go from 3 to 4, and there's no other thing to do. So it is, I can write here. So the answer is only we start from 2, go to 3, and then 3 to 4. This is the shortest path, and the cost is 4. This is the answer for part B. Now let me select this. And write it here. This is shortest path from 2 to 4. Now let's check from 3 to 2. From 3 to 2, if this is 3 and this is 2, now we are going to have from 3, this is source. So let's delete them all. This time source is 3. Destination is 2. So here we have 1, here -1, and the rest zeros. Now 1 -1 and the other zeros. Now let's delete this one. And oh, sorry, I deleted the formula. I should delete these values. Now they are all zeros, and this is also 0. We want to use the solver again by the same constraints and changing variables, objective function. If we start to solve, you'll see this exclamation mark. It says that the problem is infeasible. But still you can see that it gives us some, because we know that we need integer solution. It may give you some approximate solution, but we are not going to accept that one. So if you see this one and it says it's not feasible, then you shouldn't accept. Here also, let me see if it moves up. It doesn't move. You can see very strange numbers. In that case, say that restore original values. Click on this. Don't keep the solver solution. We don't need that solver solution. When you see exclamation mark, remove it, and your answer is going to be does not exist. So here, in this case, we come here and write does not exist. So in this case, we don't have any shortest path. So there won't be there's no path, so there won't be a shortest path either. This is how to solve the shortest path problem by converting it to a linear programming, considering this min-cost flu problem on a network, and we can solve by solver once we have a linear programming model.